this video, we're going to treat the reactor R and distillation column D1 and the pair of azeotropic columns AZ as 3-unit operations and set up the material balance equations in vector form for each. For a combined molar flow rate of feed water and recycle water streams for decanter and distillation column, 12 times that of the alkene molar flow rate. AZ decanter water mole fractions of 0.001, 0.1, 0.1, 0.8 for propylene, disopropylether, isopropanol, and water respectively, and mole fraction ratios for each of these components between the distillate and bottoms of the distillation column D1 of 100, 10, 5, and 0.2 respectively. How many equations and how many unknowns can there be? For the same feed and product specifications in Part B, the last video, calculate the total molar flow rates and compositions of the feed bottoms and the distillate of the distillation column D1, as well as the extent of reactions and total molar flows of the ether and alcohol product streams. So for this code, we're going to be working off of the last code we just did. So I already have everything imported that we need. I've also imported something called JAX that I'll get into a little bit later in this video. So the first thing that we're going to do is we're going to define our second equation in order to set up the material balance equations in vector form for each. So we're going to define, and we're just going to call this one equation 2. And our vector is going to be D because we're using a dictionary for this. So now that that is defined, let's put in our first equation. Our first equation we're going to have is going to be for our reactor feed. So let's call this reactor underscore feed. And now this is going to be equal to basically all of our feeds multiplied by their compositions as well. So just like the other video, we need to have our alkene feed, which we're going to do D dot alkene F multiplied by D dot alkene Y plus D dot water F multiplied by D dot water X plus we have to include the bottom of our first distillation column, so we'll have that as D dot D1B, and this is a combination, so we'll have D dot D1BX, the composition. Then we're going to add for our decanter. So we'll have D dot decanter W times D dot decanter W. Okay, that all looks good, I think. Okay, so now next we need our reaction. So again, let's have Rx and S, and then this still is going to be the extent of our reactions multiplied by their stoichiometry. So D dot EXT underscore RX1, just like our last video, multiplied by D dot stoic underscore RX1 plus the same thing but for our second reaction. So D dot EXT underscore RX2 times D dot stoic underscore RX2. That one looks good. So now we're gonna do our equation for our reactor product, which is the stream in the first distillation column times its composition. So let's do reactor underscore product. And that'll be equal to D dot D1 F for feed times D dot D1 Fx for composition. That looks good. Okay, so now what we're going to do is we have to put in the equation for our water alkene reactor feed ratio constraint. So let's abbreviate that. WARFR underscore constraint. Okay. Then that's going to be equal to our D dot water F plus D dot D1 capital B plus D dot decanter W. Then that's going to get divided by our D dot alkene feed. And we're going to subtract D dot our whole constant WARFR because that's what we want. That line looks good to me. Okay, so now we're going to put in our reactor balance, which is the sum of our reactor feed and reactions minus our product. So let's have this as reactor underscore balance. And that's going to be equal to D dot D1 F times D dot D1 Fx. Oh no, wait. I moved ahead of myself. Reactor balance is equal to our reactor feed, what we just did, plus our reactions minus our product. So reactor product. Awesome. Okay, so now we're going to do the distillation balance, and that's D1 underscore balance okay. Now that's going to be equal to our D dot D1 F times D dot D1 F X minus D dot D1 B times D dot D1 B X minus our D dot D1 D multiplied by our D dot D1 dy. And now we're going to have to specify the ratio of mole fractions because this is a vapor-liquid equilibrium. So we'll have D1, and for vapor-liquid equilibrium, we'll do VLE. And then that's going to be equal to our D dot D1 dy divided by our D dot D dot D1 B times, subtracting our D dot D1 Okay. And now we're going to do our AZ balance. So it's the stream going in minus the streams going out. So AZ underscore balance is going to be equal to D dot D1D times D dot D1 dy minus RD dot decanter W times RD dot decanter WX minus RD dot ether P multiplied by RD dot ether X minus D dot alcohol P times RD dot alcohol X. Okay. So now basically we need to combine all of these. So we're going to concatenate them all of these equations. And we have one that is just a number here. So we're going to need to turn that into a vector. So let's go ahead and return. And again, I'm going to use J's here and I'll get into it. But so we need JNP dot concatenate, and we need parentheses and our bracket, and we're going to do this with our reactor balance. RD1 balance, RD1 VLE, and RAZ balance. And then lastly, since we need to turn this in our constant into a vector, we're going to do JNP dot at least underscore 1D, and then in parentheses we'll put our WARFR constraint. And that one looks good. So basically, once we combine all of this, we have like a total of, we're gonna have 17 equations. And then for the amount of unknowns, if you do 17 times 17, that's 289 unknowns. So let's go ahead and run this. Okay. Now, what I've done here is, so we have 17 equations and 289 unknowns, but now we have to go ahead and specify everything that we do need. And we're going to be utilizing the same parameters that we used in the last video. So in case of, just to simply not repeat myself and to save time because I'm running out of time, I've already created the dictionary for everything we need to specify, but I'm going to go over it. So we have our dictionary, and then same thing in the last video, we have the stoichiometry of both of our reactions. We have the feet of our alkene, that composition, the feet of our water, that composition. We have our arrays for our ether and alcohol, and then I've also put in here that we have our water alkene reactor feed ratio set to 12. And then down here, basically these are still unknown, so we've put in ranges and compositions, but they still remain unknown. So these are basically our initial guesses, and then it also has the lower and upper limits for each of the distillation columns, the decanter, and I also have the ranges for our ether and alcohol, the separation ratio here, and the extent of our reaction ranges as well. So by using that as a dictionary, now basically we want to wrap all of this up. So if we wrap all of this up, basically it's going to return 5 elements. Now, the first element it's going to return is x naught. Now, x naught is basically the vector of our initial guesses. Then next we have x2 and t, and this is going to be a function for x naught. Then we have wrap, which is the function to actually wrap the equation. Then we have x2 u and k, which is for unknown, and basically this will grab those unknown variables. And then lastly we have const, and that basically covers the constant values. And this is going to be equal to d2 and t, and then we're going to put e for our dictionary. So let's go ahead and run this. Okay. So next we're going to actually go ahead and set up a name for our wrapped equation and set that equal. So let's call it wrapped, and we need our second equation. So EQS2, and that's going to be equal to that function wrap of that second equation, EQS2. So let's go ahead and run that to wrap it. Okay, so now all we have to do is we're going to utilize the root solver. And this is a very complex problem. So because of this, that JAX that I imported that I was talking about, basically it's a Jacobian. And we have to supply a Jacobian in this problem because basically what it does is it creates a function that solves for all the unknowns, which we need. So for a root function, let's have our solution be equal to root of our wrapped equation EQS2, and then we just need our x naught, and then now we need to put in our Jacobian. So let's have GAC is equal to JAX dot Jacobian, and we need that to apply to our wrapped equation 2. So, and then we need to actually print this. So let's do print our solution. So let's go ahead and run this. So basically this is given to us, but this is all a mess. I'm not really sure what that means. So to make it easier for us, let's go ahead and convert the x values into a set of values that makes sense to us and covers all 17 of our unknowns. So to do that, let's just grab the unknowns. So let's do x2 u and k, which is for x2 unknowns, our solution, and we only want those x values, so we'll pull those, dot underscore as DICT empty parentheses. So if we do this and run it, it should give us by what we defined each name to be